Okay, continuing with our discussion from the last lecture on growth kinetics, we had divided growth kinetics into two processes depending on whether long range diffusion is a rate controlling process or not. If the long range diffusion is not a rate controlling process, then we get what is known as interface controlled growth. And if the long range diffusion is the rate controlling process, then what we call as the diffusion controlled growth. So, today we will review what we had done in part 1 of this course, the interface controlled growth first. So, in interface controlled growth, for example, gamma iron, which is a face centered cubic structure, on cooling below 910 degrees centigrade transforms to alpha iron, which is a body centered cubic structure. So, this is a single component system in which a growth of a alpha nuclei that forms in gamma iron then grows via the mechanism of interface control growth that we had seen in the last lecture. Now, in order to get to the growth kinetics under interface control, we can look at the what is the barrier involved in jumping of an iron atom from the gamma side to the alpha nucleus, the alpha stable nucleus that is formed for it to grow. So, the barrier to jump is delta GD. So, this is the jump barrier from for an iron atom to jump from the parent gamma phase to the product alpha phase. If I look at the overall change in free energy that is involved in the process of growth from gamma to alpha. So, let us look at this diagram and understand this. This is gamma iron and this is alpha iron, which is at a much lower energy state than gamma iron, and that is why the ferrite or rather the body centered cubic iron should form from the gamma phase if the temperature is less than the transformation temperature, that is 910 degrees centigrade. So, what is the barrier to jump for an atom from the parent gamma phase to the product alpha phase? This barrier is what we have called as delta GD. So, this is the energy hill that is involved for an iron atom to jump over this barrier, and beyond this it will simply go down to a much lower energy level. And what is the difference between the energy level of gamma iron and alpha iron? That is simply, we already know, is the volume of the product phase multiplied by the absolute value of the volume free energy change. So, hence clearly the thermodynamics favors the jumping of atoms from gamma to alpha. Now, if we wish to now compute or rather estimate or calculate what is the rate, or rather what is the net jump rate of atoms from gamma to alpha. We can figure that out, and let us call that as dN by dt, the net jump rate. The net jump rate would be the difference between the forward jump rate of atoms from gamma to alpha minus the backward jump from alpha to gamma. So, for atoms to jump from gamma to alpha, the energy barrier is only delta GD, while for the atoms to jump from alpha to gamma, the energy barrier is sum total of delta GD plus V times the absolute value of delta GV. So, writing this down, Ns, which is the number of atoms that is surrounding the alpha phase, as we had seen in the formation of the stable nuclei also. Ns is the number of atoms that is surrounding in the gamma iron surrounding the alpha iron. These are the atoms that can jump from gamma to alpha, multiplied by the Debye frequency, multiplied by e to power minus delta GD by KT. We have already seen such kinetic expressions being written in the last lecture. So, this is the forward rate. There will be some number of atoms that can jump from alpha to gamma, but the energy hill is much bigger for them, and hence the backward rate would become Ns nu e to power minus delta GD plus V times delta GV divided by KT. This constitutes the backward rate. So, the difference would give you the net jump rate in the forward direction from gamma to alpha. So, just simplifying this a little bit, dN by dt now can be written as Ns nu e to power minus delta GD divided by KT multiplied by, I have taken this term common, I can write this as 1 minus e to power minus V delta GV divided by KT. Now, instead of writing this rate in terms of number of atoms jumping from gamma to alpha, we would like to convert this into a growth rate in terms of measure of distance. And hence, if I consider a spherical nuclei which is growing, then its radius of change, which is dr by dt, which we can also call it as the velocity of transformation in terms of meters per second. So, dr by dt can be written as, in a very similar way, lambda nu e to power minus delta GD divided by KT and the same bracket term 1 minus e to power minus V delta GV divided by KT. Here lambda is essentially atom to atom distance, and hence we are able to now write growth in terms of a growth velocity. So, this could be considered as a growth velocity. If I look at this expression, we can try to see what happens for small driving force. Small driving force means that the term V delta GV is much smaller than KT. Now this, if we had a very small driving force, then I can simplify this and write the velocity or the growth velocity as simply lambda nu e to power minus delta GD divided by KT times velocity multiplied by delta GV upon KT. That is, the term in the brackets can be approximated by V delta GV upon KT. For large driving force, the growth velocity becomes, for large driving force, this term becomes very small, much smaller than 1, and hence that this term can be neglected, and hence the growth velocity simply becomes lambda nu e to power minus delta GD divided by KT. Now looking at any of these expressions, whether this expression or this expression or this expression, there is one conclusion that we can draw directly from here, and that is that the growth velocity is not a function of time. So for a given temperature, growth rate is a constant. So one major conclusion regarding interface controlled growth is that at a given temperature, growth rate is a constant. Now let us examine. We have seen, we have briefly reviewed how interface controlled growth works. Now let us examine and compare this with diffusion controlled growth, which is a little bit more involved, as you shall see. So looking at diffusion controlled growth, so examples of this, one important example of this is austenite transforming to ferrite or pearlite. So for that matter, diffusion controlled growth would be present in many alloy systems where long range diffusion in the parent matrix would become important. So consider a hypothetical binary system AB let us say that we have an alloy AB of composition C naught on this phase diagram, and we heat this alloy to a temperature of T1, so that the entire sample is a single phase sample of, let us say, alpha phase. We suddenly quench this sample, or we rapidly lower the temperature of this sample to some temperature So, we go from T1 to T very rapidly, effectively in no time. As a result, we reach this point, however, no transformation is taking place and we get a supersaturated solid solution of B in A. And let me mark out the equilibrium composition that are expected at T. We expect to get an alpha phase of composition C alpha at beta precipitation of composition C beta. So, this is the two phase alpha plus beta phase field. Now, looking at this system, we have at time t is equal to 0. Let me draw this diagram separately. That if I look at, I am going to look at one dimensional growth of beta in alpha. So, at time t equal to 0, when I rapidly change the temperature from T1 to T, I have alpha everywhere of composition C0. After some time T, I will get a following situation. I will get some beta that is formed of composition C beta. So, I have a linear growth of the beta phase, and beyond this, this is the distance x, and it has grown by a distance x for some time t greater than 0. Let me also mark out, if this is the composition C naught, let me also mark out the composition on this diagram of C alpha. Now, what we expect is that in this region, beta will have the equilibrium concentration dictated by the phase diagram of C beta. Very far away from this alpha beta interface, my composition is going to be C0, but locally we will have equilibrium. That means we expect at the interface the alpha composition to be of C alpha, and as we go away from the interface into the alpha phase, the composition will move towards C naught, and I can draw this concentration profile within the alpha phase something like this. So, this is at some time, let us say T1. Now, after some more time has elapsed, the beta will grow further by, let us say, a distance delta x. Hence, now the composition at this new interface of alpha beta, the local equilibrium will hold, and the alpha composition at the new alpha beta interface would be C alpha. But as we move into the alpha phase, there would be a concentration will move towards and well within into the alpha phase we will again reach C naught. So, that is how the beta phase will keep growing and the concentration profiles will also change. Now, once we have this this picture, this model of the growth of beta through a diffusion controlled process, which means that now B atoms have to diffuse over long range from within the alpha phase to the interface, and then those atoms have to jump across the interface to enable beta to grow into the alpha. So, essentially the growth is going to be controlled by the time it takes for the solute atoms to move from large distances in the alpha phase right to the alpha beta interface. So, what is that? How can I calculate at what rate there would be the atoms will be moving? That is simply given by the Fick's first law, that the flux of B atoms in the alpha phase would be given by the diffusion coefficient d times the concentration gradient in the alpha phase dC by dx. Now, these profiles, the concentration profiles that are shown here in this model, these are the actual concentration profiles that are expected, and their functional dependence can be obtained. In fact, the solution to this concentration profile is the error function. Now, that makes the calculation derivation on this model to be quite complicated. Hence, we make a very simplifying assumption, and that simplifying assumption is as follows, that instead of taking these kind of concentration profiles, we assume that the profiles can be assumed to be linear in the alpha region, like this. Therefore, the flux J then becomes a constant at all x, and that makes the subsequent derivation very simple, and that simple model also gives us very close to the actual picture that is shown in the model. So, using this the flux equation, and also knowing that invoking mass balance, that no mass is added or lost by the system, using these two we arrive at the following expression for velocity of the interface. So, velocity of the interface V is equal to dx by dt is given by the diffusion coefficient d times C0 minus C alpha square upon 2 times C beta minus C alpha times C beta minus C naught times 1 upon x. This equation was derived in detail in the lecture or the part 1 of this course. If we integrate this, we arrive at the following expression for x, how x or the thickness of the beta phase changes as a function of time, and that is given by C naught minus C alpha divided by square root of C beta minus C alpha times C beta minus C naught times square root of dt. This shows, this being a constant at a given temperature, the concentration C naught, C alpha, C beta are already taken from the phase diagram and they are fixed. X is directly proportional to square root of dt, and hence this is also called as a parabolic growth. And then the interface velocity v dx by dt becomes, if we simply differentiate this, as half C naught minus C alpha divided by square root of C beta minus C alpha times C beta minus C naught times square root of d upon t. That means now the velocity is proportional to square root of the diffusion coefficient divided by time. This equation very clearly shows, in contrast to the interface controlled growth, that at a given temperature growth rate was a constant if interface control growth mechanism is present. However, in the case of the diffusion controlled growth, velocity clearly is no longer a constant, but it varies as a function of time, and in fact it gradually reduces as the transformation or as the growth progresses. So, this is a very important factor to realize, that the two mechanisms, interface controlled growth gives us constant growth rate, diffusion controlled growth gives us growth which is dependent on time. What else, what other conclusion can I draw from this expression that I have written? If I look at C naught minus C alpha, this is at a temperature T, C naught minus C alpha represents the supersaturation at time t is equal to 0. That is, the growth velocity is directly proportional to the supersaturation. Higher the supersaturation, we expect higher the growth velocity. Now, the conclusion that the growth rate reduces as a function of time, why should that happen? Of course, mathematically this comes out that it reduces as time progresses, but that can also be seen from this model of diffusion controlled growth. This is at some time t1, this profile is at some time t2 which is greater than t1. If I look at the two slopes, as time progresses, the slope of the concentration profile or the concentration gradient slope is reducing. If I look at the Fick's equation which gives me the flux is directly proportional to the concentration gradient. Hence, as time progresses, the concentration gradient dc by dx is reducing, so flux is reducing, and therefore the growth velocity is reducing. Now, in the next lecture, we will briefly look at how undercooling will affect the growth rate, that as I change the temperature to different temperatures, how undercooling affects the growth rate, that we will have a look, and then we will look at the overall kinetics of phase transformation. We will stop here.